Okay, so let's look at some examples and see if we can have this make some sense. All right, so let's come back to example 2. We're looking at the limit as x is approaching infinity. In my last slide, infinity is the value of c, and we're looking at the natural log of x divided by x. So f of x is the natural log of x on the top, g of x is x on the bottom. And I can see that the form is infinity divided by infinity. So this means that I am allowed to use L'Hopital's rule. And whenever we're using L'Hopital's rule, we want to indicate that we are using L'Hopital's rule. So the way that I usually indicate that is I write a little L apostrophe H to let everybody know that I'm about to use L'Hopital's rule. Okay, everybody, I'm about to use L'Hopital's rule. It's the limit as x approaches infinity, and then I'm going to take the derivative of the top. The derivative of the natural log of x is 1 divided by x, and then I get to divide that by the derivative of the bottom. The derivative of the bottom is equal to 1. Well, there's not a whole lot going on there, so I can write the limit as x approaches infinity of 1 divided by x. That was just me doing a little bit of algebra there. And then I can see that as x is approaching infinity, this whole thing is approaching 0, so I get that the limit is equal to 0. Okay, let's see if we can find a couple more examples. Let's look at example 3. How about the limit as x approaches infinity of x squared divided by e to the x. All right, so our form of this limit is that the top is approaching infinity, and the bottom, e to the x, is also approaching infinity. So this tells me that I am allowed to use L'Hopital's rule. So I will use it, indicate that I am about to use L'Hopital's rule. So that will be equal to the limit as x approaches infinity of the derivative of the top, that's 2x, divided by the derivative of the bottom, the derivative of e to the x, is e to the x. Okay, well, let's see, what do I have? Let's look at the form again. As x approaches infinity, the numerator, 2x, is approaching infinity, and the denominator, e to the x, is approaching infinity. So I use L'Hopital's rule, and I still have the form infinity divided by infinity. Well, since I have the form infinity divided by infinity, I can use L'Hopital's rule again. So I'll go with L'Hopital's rule again. The limit as x approaches infinity of 2x in the top, the derivative of 2x is 2, and the derivative of the bottom is e to the x. And now if I check the form of the limit, the top is approaching 2 while the bottom is approaching infinity. This is now a determinant form, and the only way for this to be anything is for the whole thing to end up going to 0, because we've got 2 divided by larger and larger and larger and larger numbers, and so that tells me that the limit is going to end up being equal to 0. Okay, so we need some more examples. How about example 4? Let's look at something that we have actually looked at before. The limit as x approaches 0 of the sine of x divided by x. And you may recall that back when we were beginning to learn about limits, we looked at this one and we ended up needing it in order to define the derivative of sines and cosines. And we did this using the squeeze theorem, and it actually took quite a bit of work in order to evaluate this limit. It turned out that the limit was equal to 1. And I can actually show you that it's equal to 1 a lot easier by using L'Hopital's rule, because the form of this limit, as x is approaching 0, sine is approaching 0, and as x is approaching 0, x is approaching 0. So this limit has a form of 0 divided by 0, which means that I can use L'Hopital's rule. So L'Hopital's rule would say that this is the limit as x approaches 0 of the derivative of the sine, which is the cosine, divided by the derivative of x, which is 1. And now, as x is approaching 0, the form is the cosine of 0, which cosine of 0 is 1, and the denominator is 1. So this is a very determinant form, and I get that that limit is equal to 1. If you go back in your notes and look at how we did this limit, maybe the first or second week of school, there was a lot to write down, and L'Hopital's rule answers this question pretty quickly. Okay, so that brings us to example 5. How about the limit as x approaches infinity of x times e to the negative x? All right, well, let's talk about the form here. The form, as x is approaching infinity, and e to the negative x is going to be approaching 0. So the form of this limit is 0 times infinity. This is an indeterminate form. So we cannot say that 0 times infinity is 0, and in fact, in this case, it is not. L'Hopital's rule only works for infinity divided by infinity or 0 divided by 0. So I need to do a little bit of algebra and turn it into the form that I would like for it to be. And what you can almost always do is just take one of the things, that is one of the products, and move it down. So like e to the negative x, it's pretty easy to make that x divided by e to the x. So I just did algebra here. You'll notice that over here I did not write L'Hopital, that I was using L'Hopital's rule, because I wasn't. I was just doing a little bit of algebra. And now the form is infinity divided by infinity. So L'Hopital's rule is for 0 divided by 0 or infinity divided by infinity. If you have 0 times infinity, you can turn it into infinity times 0. And then, so L'Hopital's rule is for 0 divided by 0 or infinity divided by infinity. If you have infinity times 0, you can turn it into L'Hopital's rule by moving one of the products down and turning it into either 0 divided by 0 or infinity divided by infinity. So now I'm going to use L'Hopital's rule. And that will get me the limit as x approaches infinity. The derivative of x is 1. The derivative of e to the x is e to the x. And now the form of the limit is 1 divided by infinity. And that is going to end up having to be 0. I think earlier I said that this one wasn't going to be 0, and sure enough, it did turn out to be 0. So sometimes these limits turn out to be 0, infinity times 0, but not always.